Very good morning, students. Let us continue with the next property of DFT. So, the fourth property is circular frequency shifting. So, it is also known as multiplication by an exponential in time domain. I'll tell you what it is. So, first, let us see what is the statement of circular frequency shift. So, if the DFT of x of n it is equal to x of k, then the DFT of Wn power of minus Ln into x of n it is equal to x of k minus n with circular shift n. That is, as I told, the other name is multiplication by an exponential in time domain. That is, if you see the statement, you can observe instead of x of n, we have multiplied x of n with an exponential component, that is Wn power of minus Ln. As we know, Wn is nothing but e power of minus g 2 pi by n. That is x of n it is multiplied by an exponential term, that too in time domain sequence. If that is the case, what is the DFT of this multiplied sequence? That is what the circular frequency shift property. So it should be equal to x of k minus L with circular shift capital N. So let us prove this property. So as we know, the definition of DFT, x of k is equal to summation n is equal to 0 to n minus 1 x of n Wn power of kn. So here I am replacing this k by k minus L. So in the entire equation, wherever capital K is there, I just replaced with k minus L. So then replacing it and segregating Wn power of k minus L into n, we are getting the expression as summation n is equal to 0 to n minus 1 x of n Wn power of minus Ln multiplied with Wn power of k into n. And we know the shift is frequency shift, that is x of k minus L can be represented in terms of frequency shift as x of k minus L with circular shift capital N, which is equal to the same summation n is equal to 0 to n minus 1 x of n Wn power of minus Ln into Wn power of kn. And if you observe the right hand side of the expression, we can segregate as the DFT equation. That is, as we know, the DFT expression is summation 0 to n minus 1 x of n into Wn power of kn. And here the thing is x of n is replaced with x of n into Wn power of minus Ln. Hence, the right hand side expression can be written as DFT of x of n into Wn power of minus Ln. So, taking the right hand side and left hand side on the other areas, DFT of x of n into Wn power of minus Ln, we can rearrange and we can write it as the DFT of x of n into Wn power of minus Ln is equal to capital X of k minus L with circular shift n. And finally, you can observe the shift it is in the frequency domain, that is with respect to capital X of k. Hence, the property we name it as circular frequency shift property. That is, the shift is happening in the frequency domain, that is with respect to capital X. And here we have proved that the DFT of the sequence x of n, which is multiplied by an exponential term, it is equal to capital X of k minus L with circular shift n. So let us see the next property of DFT, that is symmetry property of real valued sequence. Here I am going to prove the symmetry property only for the sequence which is of real values. Hence it is named as symmetry of real valued sequence. And whenever you are applying this property for any problems, see that x of n it is of a real value sequence or not. So what is the statement of symmetry property? So if the sequence x of n, where n ranges from 0, 1, 2, 3 up to n minus 1, if it is real, then the property says the DFT of capital X of k is equal to x of x conjugate of n minus k, where k ranges from 0 to n minus 1. So let us prove this property. So we'll start with the DFT expression x of k. By the definition of the DFT x of k, we have x of k is equal to summation n is equal to 0 to n minus 1 x of n wn power of kn. So now let us take conjugate on both the sides. So if I take conjugate on both the sides of the entire equation, I can write x of k as x conjugate of k. And on the right hand side, summation n is equal to 0 to n minus 1. Instead of x of n, it is x conjugate of n, and instead of wn power of kn, the conjugate of that, it is wn power of minus kn. So next, in x conjugate of n can be written as x of n, since x of n is a real sequence. Hence, x conjugate of n can be replaced with x of n in the next step. So it is summation n is equal to 0 to n minus 1 x of n wn power of minus kn. So in the next step, I am adding an additional term whose value is 1. That is represented in the right side as wn power of minus capital N into small n, whose value is 1. So I am just adding it in order to prove that symmetry property. So if I am going to add, so I can combine wn power of minus kn with wn power of minus n into n. So the final expression becomes summation n is equal to 0 to n minus 1 x of n wn power of n into n minus k. So this is nothing but x of n minus k, whereas it is the expression for x of k where k is replaced with n minus k. Hence I can write the final equation as x conjugate of k is equal to capital X of n minus k. Hence we have proved the conjugate property of DFT. So this symmetry property can either be written as we have written x of k is equal to x conjugate of n minus k. It can also be written as x conjugate of k is equal to x of n minus k. Both the way you can write it. Once again, let me repeat. The symmetry property is x of k is equal to x conjugate of n minus k, or you can write as x conjugate of k is equal to x of n minus k. Both are correct. So the symmetry equation x conjugate of k is equal to x of n minus k, it conveys the message that the DFT of a real sequence possesses conjugate symmetry about the midpoint. So what is this conjugate symmetry? That is, if n is an odd sequence, I can say that, for example, I am going to take n is equal to 7, which is an odd number. So below I have drawn a diagram. You can observe there where k ranges from 0 to n minus 1. So it is 0 to 6. So k starts from 0, 1, 2, 3, 4, 5, 6 and so on. So since n is equal to odd, the property says the conjugate symmetry is about n by 2. So n by 2 is nothing but 7 by 2 here. For example, for n we have taken as 7. So 7 by 2 it is 3.5. So across 3.5 you can observe the conjugate symmetry. That is, between 3 and 4 there is a conjugate symmetry pair. And again between 2 and 5 it exhibits conjugate symmetry. Again between 1 and 6 there is a conjugate symmetry. And similarly, if n is equal to even, so n by 2 it becomes 8. So here I have taken an even number as 8. So n by 2 is equal to 8 by 2, it is 4. So across 4 you can observe the conjugate symmetry. That is, 3 will be equal to 5 and 2 will be equal to 6 and 1 will be equal to 7. That is, it exhibits conjugate symmetry. So what is this conjugate symmetry? As I told you, it is, for example, for the sequence n is equal to e1, as I told, there is a conjugate symmetry between 3 and 5. That is, x of 3 will be equal to x conjugate of 5. Similarly, x of 2 will be equal to x conjugate of 6. And x of 1 will be equal to x conjugate of 7. That is, these two will have conjugate symmetry property. So the main application of the symmetry property is when half of the sequence is given, we'll be able to find out the remaining DFT sequences using the symmetry property. That is, if 0 to 3 values are given, the rest of the values can be taken the conjugate of the other, and you'll be able to find the entire DFT x of k values. So this is the main application of this symmetry property.